Welcome to The Explainer. Today, we're taking a look under the hood of a technology that is absolutely everywhere right now, writing poems, fixing our code, and pretty much changing how we talk to computers. We're talking about large language models.
So, yeah, let's start with the big question. How is this even possible? I mean, a machine that can write a sonnet and then turn around and explain quantum physics? It honestly sounds like something straight out of science fiction. But it's really happening. And the tech behind it all is the large language model.
So, what is an LLM, really? For all the complexity and all the hype, you might be surprised to find out that the core idea, well, it's actually incredibly simple. And that's it. Seriously, that's the whole game. An LLM isn't thinking or feeling the way we do. It's a hyper-advanced pattern matcher. After it's been fed just a colossal amount of text, its one and only job is to make the best possible guess for what word comes next. It sounds almost too simple, right? But as you're about to see, this one little trick is the key to everything.
And believe me, when we say large, we are not kidding around. That word refers to the model's parameters. You can think of them as these tiny little knobs and dials the model uses to make connections between concepts. And just look at this growth. We've gone from billions to literally trillions of these things in just a handful of years. This explosive scaling is a huge reason these models have gotten so incredibly smart so fast.
Okay, but how does just predicting the next word let a machine write, say, a functional piece of computer code? Well, it's not magic, it's a process. It's a pipeline. So let's pop the hood and see exactly how our text gets turned into intelligence.
I want you to picture an assembly line. When you type in a prompt, your words start a journey. They go through all these different stages, one after another, before a final answer comes out the other end. So let's walk through this factory floor step by step.
All right, first up, tokenization. A computer can't read words, it reads numbers. So the first thing the model does is break our sentence down into little chunks called tokens. Each token gets its own unique ID number, turning our nice, human-readable sentence into a sequence of cold, hard integers. Now, each of those numbers gets turned into a very rich set of coordinates, a vector. This process is called an embedding, and it's super cool. Think of it like this. The model plots every single token onto a gigantic, multi-dimensional meaning map. On this map, words like king and queen end up as close neighbors, while words like king and screwdriver are miles apart. This is how the model starts to grasp the relationships between words. But meaning isn't just about the words themselves, it's about the order they're in. I mean, dog bites man is news, but man bites dog? That's a headline. To get this, the model adds another layer of information to each token's vector, basically telling it, hey, you were the first word in the sentence, you were the second, and so on. It needs to know the sequence.
And this brings us to the real secret sauce of modern LLMs, self-attention. This is the mechanism that lets every single token in a sentence look at every other token and figure out which ones are the most important for understanding the context. So in a sentence like this, the word was can pay direct attention to book, skipping right over the other words to understand the true subject. It's incredibly powerful. So after our input has passed through many, many layers of this self-attention process, the model is finally ready to make its guess. It produces a giant list of raw scores, they're called logits, for every single word in its vocabulary. You can think of it like a first-round vote. A high score means a word is a strong candidate, and a negative score means probably not. But those raw scores are a little messy, right? So a handy mathematical function called softmax comes in and cleans them all up. It transforms those raw logits into clean, neat probabilities that all add up to 100%. And now it's totally obvious. Blue is the overwhelming favorite to be the next word. And finally, the model picks a token. Usually it's the one with the highest probability, so in this case, blue. But here's the crucial part. It doesn't stop. It takes that word, blue, adds it to the end of the input sentence, and then runs that entire 8-step process all over again to predict the next word. And it just keeps doing this, over and over. That loop is how you get sentences, paragraphs, entire essays, all generated one token at a time. So, that's the how. We've seen the assembly line. But now let's talk about the why. Why does this simple process of predicting the next word result in something so incredibly powerful? Well, it really boils down to 3 key pillars. Pillar number 1 is the data. And the amount of data is just staggering. These models have effectively read a huge chunk of the public internet, trillions of words from books, websites, code, you name it.
By doing this, they're not just learning vocabulary, they are absorbing grammar, facts about the world, and even subtle patterns of human reason.
The second pillar is the architecture itself. The invention of the transformer, with that self-attention mechanism we talked about, was a complete game changer. It allowed models to process huge amounts of text and understand deep, long-range context in a way that just wasn't possible with older designs.
But this third pillar, this one is the most fascinating and maybe a little mysterious. It's a phenomenon that even the researchers who created these models didn't see coming. What happens when you just take the data and the architecture and you just scale them up, way, way up? Well, you get something called emergent abilities. And this is where things get really wild. It turns out, when you make these models big enough, they don't just get incrementally better at predicting words. They spontaneously develop entirely new skills they were never, ever explicitly trained to do. And we're talking about things like complex, step-by-step reasoning, some pretty impressive math skills, and even the ability to understand and write sophisticated computer code. Nobody programmed these abilities in. They just emerged from the sheer scale and complexity of the model. Okay, so let's bring all of this back down to earth. We've gone through the technical details, but how does all of this actually connect with us? Where do these super powerful models actually show up in our everyday lives? I'm sure you've heard a lot of these names, and they come in all different flavors now, right? You've got the massive, cutting-edge frontier models, you've got these incredible open-source models, and now you even have smaller, really capable ones that can run right on your phone or laptop.
And these models are the engines powering a list of tools that is growing every single day. We're talking chatbots, of course, but also smarter search engines, coding assistants, personal tutors. They're fundamentally reshaping how we find information and use technology.
And this quote, I think, really hits the nail on the head. The big takeaway here isn't just that we have better text generators. What we're really seeing is a fundamental shift, a whole new way of building things with computers. It's a new paradigm. At the end of the day, this technology has given all of us a brand new toolbox for creativity, for problem solving, for discovery. So the most exciting question isn't just about what these machines are capable of doing, it's about what we as humans will choose to build with them next.